I am Lulu Saleh, and I'm going to be the moderator of this session today. First of all, and on behalf of EAGE Local Chapter of Kuwait, I'd like to welcome you all to the 9th virtual technical session on the time lapse, how feasible on land seismic data. But before we get started, I'd like to inform you that this session is going to be recorded and displayed on the social media and YouTube. Also, I would like to ask you kindly to leave the questions to the end of the session. But unfortunately, as we have an issue with the chat box after the session, we will have the question and answer session, and you can raise your hand if you have any question. And now it's my pleasure to introduce our guest, Mr. Adel ElEmam. Mr. Adel is a senior consultant geophysicist with over 45 years of experience in oil and gas industry. He has masters in geophysics on attenuation of seismic waves, and he has presented and published more than 50 papers in local and international conferences and serves as a technical reviewer for several international societies. He received the SEG Honorable Mention Award certificate for his work on single sensor acquisition and processing in 2005. Also, Mr. Adel is an active member of SEG, EAGE, and SPE. He is a member of SEG Middle East Advisory Committee since 2012 and a member of Geophysicist Forum for the last 7 years. And he chaired the SEG Committee from 2017 until 2021, and currently he serves as a president of the SEG Middle East Professional Development Committee. So now, Mr. Adel, the floor is yours. You can present.
Thank you so much, Lulua, for this flattering introduction. And the talk actually is, as Lulua said in the introduction, time lapse, how feasible on land seismic data. And in fact, when I was approached by the EAGE Kuwait local chapter, I thought about what subject might be of interest for both engineers and geoscientists. And indeed, the time lapse for reservoir monitoring came on top. So the agenda for today is actually divided into four main topics. First is the seismic reservoir monitoring, and under this topic, we'll be talking about the concept, the cycle, factors affecting repeatability, parameters, reservoir parameters which affect the time-lapse response itself, processing workflows, and we'll cover also the QC attributes. I think this part will take almost a little bit more than half. Then I will go over case studies, and I will present 4 examples, 2 on the repeatability side and 2 on the reservoir monitoring side. I mean, if time allows, and then I will summarize and say something about the way forward. Okay, so there are several tools to monitor the producing reservoirs, and what I'm presenting here is a list of tools and their effective scales. I mean, in terms of spatial coverage and sampling. And in fact, every scale is important for the success of any reservoir monitoring project or enhanced oil recovery. And most actually of these projects would require to utilize a multi-physics. Some of the tools that we are looking at here measured at the well location, such as cores and well logs. Others between borehole and and surface as crosswell electromagnetic or crosswell VSP data. And other tools extend to cover a large area with lower sampling or lower resolution, such as gravity controlled source electromagnetic and surface seismic. And in fact, surface seismic is the tool that I'm going to focus during this presentation. So the broader definition and objective are we need to understand what is happening to the properties of a hydrocarbon reservoir in 3D space and in time as well. And if possible, if we can or we would be able to quantify these changes. So, in that case, time lapse or 4D for reservoir monitoring, 4D seismic, involve acquiring and analyzing seismic data at multiple time intervals to visualize the dynamic changes within subsurface reservoirs. So in that, this method provides insights into the changes like fluid movements, pressure variation, and reservoir dynamics. And the method should enable optimizing production strategies and early anomaly detection. So the 4D seismic enhances reservoir understanding, reduces uncertainty, and maximizes the economic efficiency of hydrocarbon recovery operation. We need not to forget the financial aspects when we look at any application of this method. So before we embark into the detail of the presentation or the body of the presentation, let's start with a very positive old picture. This is snapshots from almost 20 years ago of reservoir life on very well-known offshore example. And this example comes from Gulfax field, the amplitude map. And as I said, it shows the progression maps on amplitude from 1985, which represents the initial condition of the reservoir. Then water injection began in 1995, and the associated increase in bore pressure caused the amplitude change as represented by the red and orange region. The pressure has increased still further by 1999, and until to be acting as a pressure increase for that reason, and until 2003. And in 2003, the injection stopped. And by July 2003, pressure had dropped back to its normal or original state. Then in 2005, injection has been resumed or restarted again, and the pressure started to build up again in the amplitude as we see in the last amplitude map of 2000. This is really great and an excellent example of how time lapse can be of huge benefit. But how can we achieve this? The concept is simple. We have an early stage in the reservoir life. We acquire a seismic, we call it a base survey. Then the reservoir will be active for some times. Therefore, there will be changes in fluid movements, saturation, pressure, and temperature as well. Then, after several years of activities, or after a certain period of activity within the reservoir, we take another snapshot, or we acquire another seismic survey. We call it monitor survey. And then we subtract both. Then what we're supposed to get the 4D signature, or the time difference, the difference between the difference in property which occurred due to the activity within the reservoir during this span of time. This is simple, as we can see from the diagram, but in order to achieve this, we have to have several conditions for our seismic to be successful. So successful 4D project needs most important and as a prerequisite that the 4D signal to overweigh the 4D noise. This can be achieved by, we have to repeat our seismic data acquisition exact, which is not the case in as we will see later, and or to so the graph says here, acquire system or acquisition system which control the variability, means we repeat exact. If we can do that, if we cannot do that, we need to add another piece during the acquisition, which is acquisition system to measure this variability. And if we know those two both ingredients, then the time-lapse processing will be straightforward. So on the processing side, we need our processing to be robust, or we need a robust workflow to compensate for the acquisition-related non-repeatability and to compensate for the environmental effects, different noise terrains, and finally resolve the 4D signature. So this diagram actually talks about the monitoring cycle in normal 4D time-lapse study. We should follow a cycle, this cycle or a similar cycle. So a typical time-lapse project, we start with a feasibility study to determine the effect of the reservoir changes. However, it can be resolved on time-lapse seismic data or not, and the level and effort required to achieve this, how can we measure these changes? What would be the effort required to achieve this? And third, we need a cost-benefit calculation to determine whether the time-lapse project is worthwhile or not. If this proven to be the case, we move on to design a monitor survey. This is acquired and processed together with any legacy data, a 3D or a 2D legacy data, whichever is available. The results are then analyzed and interpreted, reservoir models updated, and the reservoir management strategy altered accordingly. If the results are successful, a new monitor survey is acquired as necessary during an specified interval of time, and the process would repeat. So what are the factors affecting repeatability? We say that the small differences between time-lapse vintages may obscure the desired 4D signal, especially we are talking about land data set and land 4D. We have several factors affecting the repeatability of time-lapse. One, and an issue which is one of the major issues, is the overburden, the near surface. So the heterogeneity of the overburden causes different subsurface images, may cause subsurface image due to different wave propagation. and may cause survey repetition inaccuracy. Also, the changes in surface and near surface between surveys due to seasonal changes like rain would create a change in the water table, which will cause time shifts between time-lapse data sets or between base and monitor survey acquired on land. Infrastructure and obstacles, especially, most of the time-lapse are done within oil fields, where oil fields are regularly see lots of changes on the surface in terms of development and infrastructure. Acquisition systems, we need consistent differences between surveys, and the variability within the survey also might cause difference. Different types of multiple types and terrains also may affect our repeatability measurements. The noise is another big issue, and the different terrains and the different noise, different seasons, ambient and source-generated noise, man-made noise also would be a factor affecting the repeatability of our data. So, one of the inexact repetition of source and receiver location causes a number of problems. The first and most difficult or intractable one is the fact that the overburden distortion differs between surveys. Near surface statics may exhibit rapid spatial variation that may not be comprehended by near surface models. Noise content, as I said before, related to surface waves and scattering in the overburden will differ. And we risk differing sources and receiver coupling. That's another big issue. A given vibrator point might be on a bedrock, whereas a vibrator only a few meters away might be in a soft channels fill sediments. This example shows such a case. Then, again, the variation in the depths of the water table from one survey to the next will cause differences in the near surface statics. Correlation between signal and noise ratio and rainfall have also been observed in several surveys, suggesting that the soil saturation has an impact, presumably by affecting coupling of sources and receiver. In addition, near surface scattering and surface waves will vary from survey to survey if the near surface properties changes. The map on the bottom shows the viscosity attribute of the vibro size, where it is clear the difference between the two maps, mainly on the western side, which indicate that the near surface just below the vibro size is different between the two base plates and between the monitor and the base survey, causing observed differences in the energy, or in turn will cause a difference in the energy propagating from each vibro size into the subsurface layer. The next slide illustrates these effects on seismic data. Although, when we look at these shot gathers visually, both shots from the base survey and from the monitor survey are very similar, almost identical, but the variation appears and became more obvious on the difference plot, where the difference in the near surface statics, the difference in the signal to noise ratio, the difference in types of different terrains of noise are very apparent on the difference plot. So again, we are still on the factors affecting repeatability, acquisition system. We need a consistency between the base and the monitor survey, but differences between surveys may due to source type, instrument, receiver response, offset range, azimuth difference, source and receiver line spacing, and also we may have variability within the survey, irregular source signature and receiver response, inaccurate navigation data, irregular coverage. And as we will see later, we will be correcting for all this, and not only correcting, but QCing, at each step to ensure the perfect repeatability at the end. Again, this is an example which shows that for marine survey, water layer thickness variation causes variation on the water layer multiple created by the water column. For land data, ambient noise change and difference between rainy and non-rainy seasons, infrastructure will create different terrains of noise and ambient noise. So this is factors, what we were looking at, factors affecting the repeatability itself. But what are the reservoir parameters which affect the time-lapse response? So the reservoir condition may change in several ways. The first, replacement of one pore fluid by another, which will cause a change in velocity and density, leading to a change in the acoustic impedance. We have a change in pore pressure. Pore pressure changes also causes velocity changes within the reservoir. Compaction is another factor. Temperature changes is a factor, usually not on the top of the changes, but it's a factor affecting these changes may occur simultaneously or together to reinforce each other, or sometimes they act opposite to each other. So the processing, when we go and to process the data, we actually, have to be very careful about how we QC the data. We have been looking at the factors affecting the repeatability and from the source, receiver, the geometry, everything related to the data itself, the seismic itself. So what we need here is how to QC the data. And what we need is actually to compensate for the non-repeatability. And this is done through two ways of quality control. The initial and the global. The initial quality control actually deal more with the acquisition system and the geometrical quality control, while the global QC it's performed on the seismic itself and related to the seismic, as we will see later. So when we talk about the initial QC, we need to uncover sources of non-repeatability as early as possible in the acquisition stage, address the problem, and identify the algorithms to compensate for that. From the global QC, we perform after every measure or every processing step to ensure repeatability is increasing after applying each processing step, and it's performed on the gathers and on the 3D stacked volumes. This example actually is from recent project that we have conducted in KOC, where I have listed the major processes on the processing flow according to their domain of application. So we see some processes on the cross spread and the shot domain, highlighted in gray, and on the OVT domain, as well as on the stack. And along with the QC step for each location. So at the noise attenuation, the robust surface consistent decon, at the statics. So the right, that shows, where, the major processes and the main QC steps, which we call it global QC steps. The right-hand side actually shows a list of QC attributes used at the shot and the stack, and the difference also, to ensure that we are not deteriorating the 4D signature with each processing step, as I mentioned later on. And these are the most common attributes we use for during the QC of the processing, and to assess the repeatability of the seismic data. And the most common and widely used is the normalized RMS differences and the predictability. So far, we have looked at the 4D time-lapse concept. We looked at the monitoring cycle, what are the factors affecting repeatability, reservoir parameters also affecting time-lapse response itself, and the processing workflow, and what type of quality control attributes are necessary to QC our data. During the next part of the presentation, I will present 4 case studies, if time allows, 2 only on the repeatability side, and 2 on the reservoir monitoring side. The first repeatability project is from Burgan field. It's the Burgan 4D repeatability test. So we have the importance actually of this repeatability test, that it was the first repeatability test to be done on land using point source, point receiver acquisition. So the base survey was acquired in 2015, and the monitor survey in December, about a year and a half of interval between the base and the monitor. And it's an exact geometry and acquisition, the same acquisition system, and the same geometry has been used. The study area covers, as shown on the yellow square in the middle, is it is 144 square kilometer. And of course, the objective is to assess the survey repeatability as a prerequisite for any future successful time-lapse interpretation, and to generate a pair of repeated 3D seismic volume that are sufficiently similar for reservoir changes to be detected or mapped, and to understand the impact of acquisition and the environmental parameters on repeating similar seismic on land. The statistical plot for the source and the receiver on the left bottom showed that the repeatability, or the occupying the same location for the source, were almost 99%, while for the receiver 99%, and for the sources 97%. This is definitely due to the infrastructure within the field itself. So these are the parameters used for the acquisition parameter. It's 100 by 100 receiver and source line. The fold is 3,600. Bin size is 6.25 by 6.25, and it's a full azimuth data set. You have all the parameters you can review. It's very high resolution, high density acquisition. So ideally, the area, I mean, what we are looking here is the base survey, final stack from the base survey and from the monitor survey and the difference. And ideally, the area above the target zone, which is highlighted on the difference, should have a minimal to no difference. However, due to the factors we have been talking about, especially the variation in the near surface, which we have in that part of the country, huge variation in the near surface and different types of noise, we can see that there is energy in the difference display still leaking. So this is a repeatability test. There was an early study done in KOC for the 4D seismic simulation for one of the Burgan wells for the reservoir Wara Burgan, which is a clastic reservoir, and the study. This was done as a pre-feasibility before the repeatability test, showed that I think that they have used, in this example, 70% water saturation and 15 feet of water flood thickness. The results confirmed that the 4D seismic response is about 19% of the level of the input seismic. And with 12 millisecond time shift. The synthetic seismic, according to this study, the synthetic seismic generated with the 25 hertz Richter wavelet gives frequencies sufficient to resolve the 15 feet of water flood thickness. The normalized RMS amplitude derived from the 3D seismic repeatability test showed that it can detect 4D signature of 14% or more, which encouraging in relation to the feasibility study done earlier. And that actually, would be, taken into consideration the parameter used in the study, which is the 70% water saturation and only 15 feet, which I think it's very on the low side. But this is very encouraging result from the repeatability so far, and confirms that 4D can be of future positive impact for the development of the Wara Burgan reservoir in Burgan field. So in conclusion, we say that the processing workflow successfully reduced the non-repeatable noise below the level at which the 4D signal can be observed. The study also shows that for land data, the near surface condition play a major role in the quality of the 4D. It plays a major role not only on the statics but also on the imaging side. 4D attributes showed that the processing sequence improved repeatability between the two data sets. The repeatability test shows that changes in the reservoir parameter, which will cause a seismic response to change by more than 14%, can be detected. The rock physics and synthetic feasibility study support the results from the 4D repeatability test. The second example is from North Kuwait, from the Raudatain field. And in fact, this is a test of repeatability between two completely different 3D seismic data sets. So the motivation, actually, I will try to go faster. The motivation here is it possible to use base and monitor surveys with different acquisition parameters for successful 4D? Can the advances in data processing eliminate the non-4D related differences between these two data sets? So, as I said, the challenge is mainly that these are two data sets are completely different equipment, different receiver change. I mean, the time between the two are more than 20 years between the two acquisitions. So, base, we can see on the left-hand side, the base study acquired in 1997 as a break pattern conventional acquisition system, while the monitor acquired in 2014 with full azimuth and high density point source, point receiver data. And the cross-spread shows that, I mean, we have a very narrow azimuth on one side and the full azimuth for the monitor survey on the other side. So the major processing step in that case, as we will see, is the 5D regularization, where the new 3D, where a new 3D geometry were designed to harmonize between the difference in azimuth between the two surveys. So the idea here is to use the 5D interpolation to try to come up with a common geometry for both surveys. And that was the objective of this test. So this is an example of the final stack between base and monitor survey and the difference. And with the two windows plotted in the difference plot. And as we see, I mean, from the next slide, as we will see from the next slide, that the processing workflow, in fact, reduced the noise above the target zone. However, the remaining noise make it challenging to discriminate noise from 4D signal, especially it's a carbonate reservoir. However, if we take into consideration the extreme differences between the surveys, the survey geometry, and the oil field infrastructure and the condition, and the land use differences between the two surveys, I believe that the workflow successfully reduced the non-repeatable noise. This can be observed in the window of attributes above, where we can see that in window 1, I mean, we are approaching to almost, I mean, the correct, it's not perfect attributes, but it is converging into the right direction. So in conclusion, we say here that the processing workflow can minimize the 4D difference, the 4D noise, and enhance it. That's a general statement. The 4D noise can be reduced with such a processing workflow, but the 4D signal should be high enough to be detected. In that case, it was questionable. Land environment adds more challenges to any 4D study, combined with different geometry and acquisition system when they are different. the fourth study became even more challenging. The study prior to the 4D analysis can give an idea if the 4D analysis is possible or not. We did not do that as we have done in the Borg, and the over-the-shelf data is costly and it can be successful. And the thing we will be looking at the way forward at the end of the presentation. The next example actually is an actual monitoring study which has been conducted for heavy oil production and the lower Fars formation of the Kuwait. They have in the start of the production, the key station on CSS over a small pilot area in the field. That with the intention that later on for full steam flow. So the objective of this study, of this monitoring study, is to map the steam side extent to check the integrity of the cap rock, and also to try to map with the surface seismic the lower Fars reservoir, if possible, to get properties through that. So the diagram on top shows how the CSS works. It's only in one well you inject the steam, you leave it a while, and then you produce from the same well. And the area highlighted the section below shows where steam has been injected when the F1B layer of formation. So this is a map which shows the 13 wells within the study area. Actually, the seismic that we have acquired is almost less than 1 by 1 square kilometer. We see that parameter. The two acquired in around January, and the monitor in March. So January 17 we acquired the base survey, and in March we acquired the monitor survey, and along with that we acquired a VSP, 3D VSP. So the color here shows that the state of each well from in terms of whether it was on the steam injection in red or on the soaking in green or the production in blue. And the last column shows the amount of steam injected for each well, and it is worth noticing that the amount is varying between wells and another. I will come back to this later at the end of this example when we look at the 40 of each well in more detail. So this is how we design our seismic. It's a very dense, very high resolution. Just to say one word here, if you can imagine the subsurface bin size is 2 by 2 meter. What we are looking at is the full area covered by the surface seismic in blue, and in the red this is the 3D VSP. And there is also more dense sources acquired for the 3D VSP in order to get better illumination on that side from the VSP. So that's quickly, how did we acquire this data? By the way, the sweep actually is from 160 Hz, which is very important and very good for illuminating the neat surface. There are 5 inlines. Each passes by a well, as highlighted in the top right corner, colored. And I would like you to, in the comparison, to look at the target area and where we can see some indicate some sagging and the change in the velocity, which is very obvious and clear on the stack itself. This will be more clear. That's a big story now. Okay, now, this is the base, pre-stack time migration time slice, and the reservoir F1B, the inline, and the surface, the acoustic impedance on the right-hand side. And this one is the monitor. I think there is a mistake on both are written base, but it's base and monitor. So I will flip between the two. And you will see the difference in the signature, the change in the properties due to the steam injection, and however it's on the early stage or later stage or in the production stage, they are affecting at each well the response of the seismic, and the time-lapse response are varying at each well, as well as on the acoustic impedance side, and also on the inline itself. We can see the sagging and the lower in velocity at the reservoir level. Of course, these changes which we talked about is dependent also on the amount of steam injected into each well. The second and major objective was to look at the integrity of the cabrock, the shell cabrock, and what we are looking here is time slice on the right-hand side within the reservoir, and we can see the activity, we can see the response of the injection and on the production of from the reservoir compared to the very smooth surface above the reservoir, which means that no abnormal activity observed from the steam injection above the reservoir and at the cap shale level. But this does not mean that where there is no risk. This is the case as per the amount of steam injected and as per the pressure of steam also used for the injection. So, as I said, we come back to that graph again, and we will be looking at the group of wells, the blue ones first, and they were, that were during the production stage, and what happened at the base and the monitor, and then the green ones, which they were on the soaking stage, and then the red one, which they were in a very early stage of injection. So this is the first group of data, and you can appreciate the difference on the bloom on each well and how it is varies due to the production. the same, I mean for the soaking period and before steam injection, or exactly at the steam injection stage. So in conclusion, surface seismic can successfully detect steam-induced anomalies on base and monitor data set. The 4D attributes, which I didn't show here, showed consistent results. VSP inversion also confirms anomaly comparable with surface seismic anomalies around one of the wells, which is well 57, this one in the corner of the plot, northwest corner of the plot. Integrity of the cap shell, as we said, could be confirmed from inversion of both 3D VSP and surface seismic. Further analysis required to fully understand the observed characteristics of the anomalies in relation to the cyclic steam model condition. The last example actually is a quick one, and it's not from Kuwait, and I'm not going to spend much, but it is time-lapse image where we show CO2 injected at Sleipner. This is in offshore Norway, injected project. And it's one of the first the first world industrial offshore CCS project, more than 16 metric ton of CO2 injected since 1996. They have used the site to monitor the survey and to quantify the free CO2 mass changes and the plume geometry, and in fact, I mean, the picture is worth more than a million of words. I mean, it shows that indeed, I mean, time lapse can be an excellent tool to for any future carbon capture storage project. So in summary, this is the summary. I will not go over it in detail, but it's a well-established technology, requires accurately repeated time-lapse data set and very careful seismic processing. It can supply uniquely valuable information about reservoir, monitor location of identify unswept targets for drilling, for infill drilling, future infill drilling, monitor and quantify gas changes for future CCS or CC. And it's a good support for reservoir management for more profitable and safer operation. And new recent advances in acquisition and the processing can improve the results in a cost and the quality manner as well. So successful 4D projects needs 4D signal, as we started with this statement, to overweigh the 4D noise. Repeatable seismic data acquisition, we need to have a repeatable seismic data acquisition. We need to have a robust seismic processing workflows to compensate for the acquisition related non-repeatability in source, receiver, geometry, and whatever, and to compensate for the environmental effect, the noise, and resolve the 4D signature. A multidisciplinary involvement of all experts each stage of planning, execution, and interpretation is very crucial and indeed required. Advanced technology may relax partially the above requirements. As an example, and different implementation which might be used in the future to relax for exact geometry and repeat exactly the acquisition, which is a luxury actually, which we are not experiencing this luxury for so many reasons. One of them, I mean, on the marine side, I mean, you acquire, you have a base acquired using a towed streamer. Now, I mean, we are going to develop better the reservoir, and the OBN survey is the tool to be used for full azimuth, higher resolution data, and definitely we have completely two different systems. The same actually applies on the land side. The same applies on the land side. I mean, when we used to acquire conventional hardwired acquisition, and now we are acquiring point source, point receiver. So the examples here shows this is the current. That's this workflow is actually the current flow of technology that we are, or the standard or the most common used time-lapse workflow, which heavily depends on the acquisition to be identical. And as I said, we know that this is not and will never be the case. So instead, in this, sorry. So and lead this, which has the capability to update this velocity on the fly as part of the inversion process. When the velocity is updated and on the basis of reflection tomography, we call it, or the Eric and his team call it the migration inversion, or GMI. Then what we are on the reflectivity side rather than on the seismic side. The same concept by Western Chico. I mean, they call it depth domain inversion, or DDI, where, I mean, you have from the two surveys, we create a velocity model, tomography, FWI, or a combination. And this velocity in depth should be optimum. And we forward model to output the point spread function a certain grid. So now, I mean, you can have two different acquisition, but I mean, the point spread function will be produced on a certain grid, completely different from the input data. The next step is to decompose this point spread function with the image migrated with to get reflectivity for each survey, and then the difference. You may think about it, you may get the difference on the PSFs and deconvolve it with the image to get the reflectivity, or to deconvolve the PSF with the image and to get two reflectivities and then to subtract. So by doing this in both cases on the DDI or the GMI, we are removing the effect of geometry differences and end up with the reflectivity, and not only the removing the effect of the geometry, but also removing the effect of the wavelet itself to get the right reflectivity. So a very nice green picture which states the vision of Kuwait for 2050 of zero carbon emission, which will require actually utilization and storage CCUS. I believe that the time lapse will contribute to the success of this CCS and CCUS project, and I'm sure it will bring in common more and more engineers and scientists to work together in order to achieve this very ambitious vision and strategy of Kuwait Petroleum Corporation. Thank you, and apology for the what happened on the internet and the disconnection which interrupted the talk, and thank you for listening, and I'm ready for the questions. Thank you so much.
Thank you, Dr. Adel, for the informative presentation. But unfortunately, as we run out of time, we have to cancel the question and answer session. So I would like to ask you kindly, if you have any question, you can send it to us and we can transfer it to Dr. Adel later. Now I would like to thank Dr. Adel again for this interesting session, and I'd like to thank you all for attending. Thank you so much.
Thank you.